All right, line P3, learning task number 2, and we're going to be looking at connecting three-phase transformers. This is going to be the first out of 5 videos that I'm going to do out of this individual learning task because this is a massive learning task, and otherwise we're going to be looking at, 2 hours of video. Nobody wants that. I don't want to record it. You don't want to listen to it. So we're going to break it down into the individual connections one by one. But this very first video, you have to watch before the others because we're going to go through the conventions and how we are getting to the proper diagrams with these. By and large, people struggle with diagramming their transformers, with making the correct connections when they are connecting up a bank. Now, I just want to go and say that this entire learning task over here is based around the whole idea of connecting three-phase transformer banks. And a bank is when I have got 3 large transformers that are going to be placed together, usually inside of an industrial installation. Not common in our lower ones. In our lower ones, we just buy a single unit, drop it in, but this is what's going to happen on our larger ones. Generally speaking, when we're dealing with these type of connections, we're dealing with massive amounts of voltage and power, and if you connect them incorrectly, you can end up with catastrophic short circuits, either when you parallel onto a bank or when you come off of a bank. So we really just want to avoid that at all costs. So we're going to take care with these, but there are a bunch of conventions we can use to make our lives easier as we're going through these. Okay, first thing that we're going to talk about is we're going to go and talk about the connection diagrams. We've got 4 main connections that we're going to go over: delta to delta, Y to Y, delta to Y, and Y to delta. And all of these are going to go and follow the same conventions. We are not going to go and talk about the terms primary and secondary. We are going to go and, when we're making our standardized drawings, we are going to go and use the terms the high voltage side and the low voltage side. Now you have to understand what primary and secondary mean. Primary does not mean high voltage. Secondary does not mean low voltage. Primary just means the side that we feed power into that transformer. Secondary is the side that we take power off. So if I've got a step up type of transformer, my primary, where I'm feeding power in, would be the low voltage, and I would be stepping it up and using my high voltage as a secondary. Vice versa, if I'm doing a step down, my primary would be my high voltage and my secondary would be my step down. When we are doing these diagrams, we are doing these diagrams to a CSA standard. And the CSA standard is going to be that we are going to use the highs and the lows when we are looking at these. And what I'm going to do is I'm going to develop a bunch of diagrams off of those highs and lows. And if I have got something where I'm going from a delta to a Y step up type of transformation, I would use this diagram over here, going from a delta to a Y. I would first make this entire diagram over here, and then I would say, well, it's a step up, so I'm going to connect this to my primary lines, and I'll connect this to my secondary lines. But we'll always do the diagrams to the high and then low. Always starting with the high transformer first. So first of all, very first thing when we are going to deal with transformer diagrams is high. Okay? Get the high done first before you do anything else. Then we're going to go and deal with the low after the high. We're also going to go and have a number of conventions that are going to be represented. We are going to go and have conventions for our phasers, the fact that we're going to go and use the 1s that are going to represent the tail and the 2s that are going to go and represent the heads. As well as we are going to go and have some phasers that we are always going to be drawing in. We're always going to draw in a neutral phaser. And that neutral phaser is always going to go in from A to my neutral. We are always going to be following this convention on our high side. We're going to be going A, B, C in that type of a triangle over there, and we are always going to be looking at the neutral as being the point in the middle. Whether or not it's a Y or a delta, it's always going to go and have a neutral in the middle. Even on a delta, there is an implied neutral that the whole system is balancing itself around. That is going to be at the very center of that. So we're always going to deal with drawing the A to N, or in other words, a phasor that's going to go across from here to here as our very first phasor that we're going to do. The other phasor that we are going to do is going to be my A to my B. We are always going to go and do a phasor that's going to be like that, and then we just do basically a connect the dots after that. Let's also talk about transformers. Figure 2 shows you two different types of transformers. We've got subtractive transformers and we have got additive types of transformers. We come up with these terms, additive and subtractive, just when we connect them as auto transformers, and whether the primary and the secondary are going to be subtracting from each other or whether they're going to be adding together. We're not going into auto transformers yet. We will later on. But if you need to go and refresh yourself as to why they're called additive or subtractive, go back to your level 2, take a look at transformers again inside of there. Otherwise, just use this simple memory trick to go and keep them straight. If I have got an additive transformer, I see that my H1 and my X1 cross over the sides of the transformer. I'm crossing over just like a plus mark crosses over itself. That's how I keep them straight inside of my mind, is that if it's an additive polarity transformer, that additive polarity transformer is going to go and have its one subscript that is going to go and cross over, like that addition mark. Subtractive ones don't have that. Subtractive ones, I see that my 2's are directly lined above each other. I see that my 1's are directly lined above each other as well. Additive versus subtractive makes no difference to the way that, well, I shouldn't say no, but almost no difference. And for us as electricians, not in the engineering profession over here, it doesn't really make a difference whether we're using one or the other. We just have to be careful about our connections and make sure that we do them in a proper manner so that we don't accidentally screw everything up later on. Okay, the next thing that I'm going to talk about is just that we have got a whole pile of figures going through from figure 3, 4, 5, and 6 inside of here is going to go and take you through 3, 4, 5, 6, a bunch of steps to go and create the voltage diagram. Rather than going through on the pictures, I'm going to go through on just a larger blank sheet over here so that we can kind of see what the steps are, and I'm going to explain them. Figure 3 is the very first thing that we're going to go and start with. Very first thing that we are going to start with is we are going to start with the fact that we are going to go and have a triangle. On my high side, that is going to be A phase, B phase, and then my C phase. So we start with this implied triangle. The second thing that we're going to start with is the fact that I'm going to go and have a neutral that is going to be placed in the very center of that triangle. Okay, A, B, C, and then the neutral on the inside. What we do is we start with this 30-degree A to neutral over here. So we'll start right now from the ground up. I'm just going to start with the A right now. And then if A is my point of origin, thinking back to, when we have quadrants, 30 degrees off would mean that I'm going to go and have a line from A to neutral that's got to be at 30 degrees over here. So I'm going to go and have a neutral point that's going to be drawn in right over there. That's what we are seeing with my very first figure, figure 1 over there. We're going to get to all of these numbers in a second, so let's just not worry about the numbers yet. We'll do all of the numbers afterwards. The second thing that I have to do is I have to go from A to B at 60 degrees. Okay, that's going to be 60 degrees over here. So I'm going to go and have my B, then that is going to go and end up here. Oh, wrong color here. There we are. I'm going to go and end up with my B. That is going to go and end up top over there. And then last of all, I'm going to go and have my C, which will apply in later on. But for now, let's just go and start with these conventions. A to neutral happens first. A to B happens second. And once I have got these points laid out, A, B, and N, I can start to draw any type of a diagram, Y or delta. Today, we're focusing right now on the Y type of connection. In a Y type of connection, I do have to have a connection to the neutral. So I'm actually going to go and connect my A winding across to my neutral. I'm going to draw that in as a red over here. And we are going to go and have our high voltage winding. Remember, we always start with the high voltage winding first. That means that I'm going to go and start with A1 over here. It's the very first one. The next one that I'm going to go and do is going to be my B. Drawing in our B winding, we're going to go and do the same thing. We're always going to go and start with my B1 end. That's going to be up top over here. And then we're going to go and draw the other end of it through and down to my neutral. I'll just draw that in just a little bit better right over there. Last of all, we are going to go and draw in my C winding, which is going to have to be 120 degrees away, and we're going to go and do the C winding the exact same way, C1. Now that we have got all of the ones placed, we know that opposite end of our high voltage windings are going to go and be a 2. If I've got an H1, I'm going to go and have an H2 winding that's going to be at the opposite end. So I'm going to go and have my 2s for each of these that we will go and place off of these. C2 and my B2 and my A2. Like that. This is beautiful. Now that we've got this first one connected over here, I'm not going to bother putting in a bunch of arrowheads off of these ones because we're looking at the connection, not so much looking at the directions of the phasers. As long as I have got consistency in my connection, and as long as the consistency is that wherever I have got a point on one of my triangles over here, this A1, that I'm going to go and make that connection across like that, I know that my A2s are all going to be tied together. The next thing that I'm going to do is I'm going to go and duplicate this drawing. Now that I have got one drawing done, I'm just going to duplicate it for my low side because we're looking at a Y to Y. And really what's happening is this. I'm going to draw a shorter line right next to each one of these that we have, because I want you to go and envision this as if it were an actual transformer. In an actual transformer, the two windings are going to be placed in parallel, like that. Which means that what we're going to do now is we are going to go and just take these individual connections that we have. We know where our A windings, B windings, and C windings are. We're going to take these low voltage connections and we are going to go and drag them out, and we are just going to go and place them. So they make connection with each other. And there we have our low voltage windings. Just note how they were all in parallel before and we just dragged them over and made those connections. Because I dragged this one over from here, if this was B1, then this over here, if this is my high voltage B1, then this would be my low voltage B1 that I'm going to go and have down here. We're going to make all those H's and X's there in a minute. But basically speaking, and I'll just draw it a little bit larger now so we got a bit of room now that we've seen the movement happen, all of my ones are going to be up at the tops again. Ones and twos are going to be in the center. Ones, twos, and ones, twos, like that, that are all going to be connected together. Last thing that we're going to do now is we are going to go and take all of our A's and B's that we have inside of these, and we're going to go and replace them with H's and X's. So I'm just going to grab all of those there, erase those, and we will just replace those with H1, H2, because we always start with the high voltage side first. Then we're going to go and have H1, H2, and H1, H2 that are going to be over here. Because I've got all of my ones and twos done on the top, remember how we dragged those lines over to go and parallel them? That means that now on my secondary side, we're just going to go and place X on these. X1, X2, and X1, X2, and X1, X2. And what you should be seeing is that we're entirely parallel all the way along. My diagram for my high voltage side is the exact same as my diagram for the low voltage side in respect to where the ones and the twos are going to go and be. And now this is dealing with single winding transformers. If we had a split winding, it would have, X1, X2, X3, X4. You're just going to go and place whatever the smallest number is going to go and get dropped all the way down to the bottom. You're always going to go and start with 1, and then you're just going to work your way through. If it had X1 through 4, then we would have an X2, X3, and then an X4 down here or something like that. We'll cover those permutations with split phases in a little bit here. Okay, this goes and develops my overall diagram. What I'm going to do now is I'm just going to go and play a game called Connect the Dots. And Connect the Dots really is going to be me taking these diagrams that I have and then from those diagrams running them onto actual connections. Over here, I have got transformer banks. It's a three-phase bank of additive polarity transformers. I know that it is additive because when I take a look at it, I see that my ones cross over here. Couple of conventions when we're drawing transformer banks. When we are drawing transformer banks, we are always going to go in place, we are always going to go and view them from the high side, okay? Even though right now we are viewing it from the low side, we're going to view it from the high side. So if I were standing up here, here's my arms sticking out, I would be looking, and this would be my right arm, this would be my left arm, and I would be able to go and see that the high voltage A phase is always going to be on my furthest right, and then it's going to go B, and then it's going to go C, going across from place to place. It does look a little bit different because we're usually going to be viewing them like this, looking at them straight on with the high side drawn at the top. If the high side is drawn at the top like this, that would mean that, you know, we see the A as being over here. But always just go with that stick man up top and which direction that they would be viewing these in. So we're going to start with our A phase, our B phase, and our C phase. Second convention for drawing transformers, something you learned back in second year, which means, of course, you remember it, that H1 is always going to be drawn on the top left-hand side of any sort of a transformer that we're going to do. And then everything else just follows that. H1 goes across to my H2, and then if it's going to be additive, my X1 goes across, because plus marks across each other themselves, and then the opposite end would obviously have to go and be the X2. With those conventions in place, now we're going to go and connect the dots between what we had here and the actual sets of lines that we are going to go and have. I'm going to go and draw out a set of lines that we are going to go and have here. And I'm just going to go and draw a red line, black line, blue line, and then we're going to go with this gray line, which is going to go and be my neutral. And we're going to start with this high side connection. When I take a look at my high side connection, I see that my A is going to be connected to my H1 of A, and then I see all of my H2s are going to get connected together to my neutral. We're going to talk about this neutral connection a little bit more in depth in a second, but for now, we're going to start by making that neutral connection. I don't know why, I just prefer making the neutral connection first. What I'm going to do is I'm going to go from here, and I'm going to go and make this connection going across like so. Do note that I haven't tied it to my high voltage neutral yet. Okay, we're going to go tie it in a minute, but I'm just holding off on this just for the time being because I want to go through there's a little bit of an issue with sometimes connecting on the high side. Okay, so we've got that connected over there. The next thing that we are going to do is we are going to go and connect our lines. We saw that my A phase H1 just has to go all the way up to my H1. We saw that my B phase H1 has to go up to here. And we saw that my C phase H1 has to go over here. This is all that we need to go and do for it. At that point, we are good to go for my high voltage connection. The last thing that I'm going to do is I'm going to go and connect my neutral to my neutral. And I'm only going to go and do that if I don't have anything else on there. Here's the deal. If I have got loads that are upstream, someone connected onto this high voltage bus over here, and I've got unbalanced loads, what can actually happen is if I go and make this final connection over here from my neutral up to the neutral bus like that, is that those other loads that are somewhere further out there, I'm going to draw it with green right now, is those other loads that are further out there can go and try to take whatever imbalances that they have and they can force it through the transformer back onto the neutral to try to go and balance out any sort of weird jankiness that they have inside of their operation. This can be a little bit of a danger, so generally speaking, I'm not going to connect the neutral on the supply side. I will generally connect the neutral on the low side, but it sometimes isn't going to be connected on the supply side. It's really going to depend whether or not I have got balanced or unbalanced loads. Okay, for the sake of this this course, though, what we are going to do is we are going to go and make our connections to the neutral. I'm just explaining right now, where you start to get problems sometimes in the real world. We're going to go with the theoretical connections because that is what you're going to be tested on inside of here rather than, the practical connections necessarily. Theoretical connection would be that I'm going to just take each one of these and connect these over to the neutral, regardless of what other loads I have upstream. I showed you just in my connection that I like to connect them all together, and then only if it is, necessary am I actually going to go and connect them on, because it does result sometimes in imbalances. If you have got a balanced three-phase load that you're supplying out of your transformer bank, the neutral connection is not necessary on the primary, and in some cases can cause problems. If, however, your secondary side is going to go and have some single-phase loads, as soon as you've got the single-phase loads, you are going to go and have to have that neutral connection in. So if you don't know which one it is, go with the neutral connection. But if you know for sure that it is strictly a balanced three-phase one, then you don't have to do the neutral connection on the high side. Okay, that takes care of our high voltage side. The next thing that we are going to do is we are going to go and take a look at our low voltage side for the same transformer. We are going to go and use the same lines once again. We're going to go and have my A line, B, and C, red, black, and blue that we're going to have over here. And then we are going to go and have our neutral as well. Once again, I'm going to go back to this, take a look, and I see that I have got all of my X2s that are going to be connected together. And then since I have created a neutral on this side as well, on my low voltage side, according to the Canadian Electrical Code, anytime that there's a neutral, we're going to have to go and do some grounding for it. So we're going to get into that grounding in a second as well. Going back over here, though, I'm going to go and make my connections. I saw all of my X2s go onto my neutral bus. So I just find the X2s, and it's paint by numbers, connect the dots, whatever you want to call it. We're going to drop them in. The next thing that I'm going to take a look at is I'm going to take a look at my A-phase transformer, and I'm going to go and connect it to my A line. Then I'm going to go to my B-phase transformer. I'm going to connect it to my B line. Then I'm going to go to my C-phase transformer, and I'm going to go and connect it to my C line over there. And at this point, we have got a complete connection for my transformer. The very last thing that we are going to do is we are going to go and ground down that neutral. So we're going to go and make a connection to that neutral to the earth itself. And what we're dealing with over here, this setup that we have done over here, is we are doing a step down type of transformation, where we are connecting onto the high voltage side, these ones over here, and then we are creating a low voltage side that we can go and attach other loads themselves to. Okay, going through then in your binder, the next bunch of pictures, figure 8, figure 9, figure 10, are all going to go and be just what I did there as I drew it through. They're just showing you those individual, connections as they're going through, because obviously it's a book. You can't really just draw, or the book itself doesn't go and draw. I do want to talk a little bit about mixed polarity and subtractive polarity. What we looked at, our drawing, we ended up with a additive type of polarity, and we know it's additive because we see that my ones cross over the transformer, and they were all additive crossover. We saw that all the X2s were going to go and be connected to the neutral, and this is what it looks like when we have that additive polarity set of transformers. We can do the exact same connection with the subtractive polarity. Subtractive polarity ones are going to now have the ones directly below. These over here, once again, looking at it, my X2s are still done the same. It doesn't matter whether we're subtractive or additive. X2s are always going to go to the neutral. My X1s are going to my line. X1 of A goes to the line. X1 of B goes to the line. X1 of C is going to go to the line there as well. That's pretty cool. We can do additive or subtractive. Not only that, check it out. We can go and do mixed polarity. This is going to blow your mind. Probably not, actually, but whatever. It's the most excitement that we get in this first learning task, so it is what it is. Over here, I see that I have got a couple of mixed ones, and I'm just identifying them by taking a look. This one crosses over, therefore it has to be additive. These ones are just a direct line, therefore they're going to go and be subtractive. I can go and have two additives and a subtractive. I still see that all of my high voltage sides are the same. Whether they're additive or subtractive, the high voltage H1 stays in the same location. It's the X1s that are going to go and move. And I take a look at my connections. I see that all of the connections of X2 are still going back down to that neutral connection, whether it's an additive transformer or whether it is a subtractive transformer. Last thing that I want to, well, not the last thing, but the second last thing that I want to talk about is just incorrect connections. If I flip a single one of my transformers around. If I would flip a single transformer around, we're going to go and get weird values of voltage. Over here, taking a look at my high side, I see that I've got all my H2s connected correctly. I see that I've got all of my H1s connected correctly as well. And then I take a look at my secondary side over here, and I see that I have got my first one connected correctly, X2 to the line. I see that I've got my third one connected correctly, X2 to my neutral over there. But then I see that I have got this other one in the middle with my X2 to the B line. Now I know that this transformer, my B transformer over here, does have to go and connect to the B line, but it has to be done properly, because what's happened now is we have basically taken this center winding over here and we have flipped it. We've just done an endo with it to go and bring it down into a incorrect type of setup. If I take a look at my line-to-line voltages, the line-to-line voltages are also going to get weird over here. I see that I have got one of these that is 208, and I've got two of them that are going to be 120. Technically speaking, they should all be 208 from line to line. It's a 120, 208 volt system. How does it work out like this? Well, it's because, remember, I flipped that B transformer. We see that right inside of here, that it's the B transformer that has had its connections flipped. And so if I take a look at my diagrams over here, what's happened is on my secondary side, I did my A connection correctly, I did my C connection correctly, and then I took my B connection, which is supposed to be up over here, and we're just going to label these ones over here. This is going to be my X1. This would be my X2. That would be a proper connection. But what I've done is I've taken this one and I have, ooh, come on. I have moved it down here because I connected that X1 onto the bottom. All of a sudden, I have created this thing. It's like this nasty chicken foot of death and destruction and all those other terrible things. It is going to go and have measurements. Normally, we should go and be able to measure across from point to point. Here to here would be 208. Here to here would be 208. Here to here would be 208, etc. But we no longer have these two measurements. Those are completely gone. And instead, we would be measuring from here to here, which would work out to become a value of 120 from A to B. You can see it's a shorter distance than what that line-to-line voltage should be. Same with this one here, C to B is also going to go and be 120. The only ones that are correct are going to be the A and C right now. And that's what helps us to go and differentiate these. Or if I'm doing this connection, right now I'm going through with my, meter. And if I go through with my meter and take a look at my readings that I'm getting, this meter reading is correct. These two are wrong. It's not what they're supposed to go and be on a line to line. So the meter reading that is correct is connected to the C line and is connected to the A line, which tells me that my A and C windings are correct. And therefore, by default, the one that's got to be screwed would have to go and be the B winding. You'd want to go and check this out. Single phase loads, if I had loads that went just from like B to neutral, those B to neutral loads would be fine. They would actually operate as single phase load off of here because that single phase load is only looking to go and jump across from this point right over here. Single phase load goes across to the neutral. So it would operate correctly. It would be three-phase loads that would not operate correctly. And last of all, the sum of the currents that I would have off of these would be incorrect, because now I would go and have all of these different vectors that would be adding together. And instead of me having vectors that are going to go and cancel, I would have vectors that would go and add together to form a net larger current. It would be a current that would almost double up this value that we would have over here. We don't want to see that, so we're just going to go and stay away from that. Other thing that you can do to screw these up is you can go and make a transformer that has a connection for 180-degree phase shift. And we're going to go and take a quick look at the connections. Once again, H1 is connected properly on all of my A, B, and C connections. H2 is connected properly, 2 connected properly, and 2 is connected properly. What's happened though is that on my secondary side, I have now gone and taken my X1s and I've connected all of my X1s onto the neutral. In essence, I have flipped everything along. Note that up top here, it's 2s that are connected to the neutral, therefore it should be 2s on the bottom that are connected to the neutral. I connect the rest of my lines in this one over here. A still connected to A, B connected to B, and C connected to C. Which means that as far as a standalone transformer bank would be concerned, this thing would be fine. I would have the same rotation. Loads, three-phase loads would operate off of it. Single-phase loads would operate off of it. But what would happen is if I was trying to add KVA in a lot of large bank type of situations, you're doing that. You're just trying to add on, the plant expands, and so you're going to add some more transformers to this thing that are going to help you to go and increase your capacity. If I were to go and add this system on to my actual system, what would in essence be happening is I would be connecting, or I would be changing these lines all the way across. This would be my A, this would be my B, this would be my C. And so when I would flip that switch to go and energize this transformer and tie it on, what would actually be happening is I would be doing a short circuit going across from B to B, from incorrect B, which is this one over here, over to correct B, which is this one over here. Same with my A phase. Same with my C phase would be flipped across there. And this would be a fairly significant fault. I mean, if we were looking at a 122.8 volt system, we're looking at a 240 volt dead short with almost no impedance because our transformer is going to have a ridiculously low value of impedance. It would not be possible to parallel another standardized transformer. What we're working with, note that we, at the very beginning of this, we said these are things that are governed by the CSA, the Canadian Standards Association. The whole point of transformer connections is that we are doing the standard connection in Canada, which means that if I die and you come to my site and you hook up another transformer, you're not going to die because you would hook it up to the exact same one as me without having to necessarily know that it was done that way. You can just trust that I would have done it that way, and I would trust that you would have done it that way. I actually wouldn't have trusted that you would have done it that way. To be honest, I check. Anytime that I'm paralleling, I check and I double check everything because we can end up with catastrophic failures. But the point of it is that anybody should be able to access anything, understand it, and parallel anything to these. Okay, that covers us off for our Y to Y transformer connections. The next one up is going to be deltas.